calculations and wire sizing appear correct based on the information provided and applicable code requirements. Let's summarize. Firstly, regarding wire size, the motor full load amps is 65 amps. 125% of the motor full load amps is 81.25 amps. The minimum wire size required is number 3, which has a 100 amp capacity. Secondly, regarding panel board breaker size, the overcurrent protection for single motor circuits has a maximum of 250% of the motor full load amps. The motor full load amps is 65 amps. The maximum breaker size allowed is 65 amps times 2.5, which equals 162.5 amps. A 150 amp breaker is within the allowable range. Thirdly, concerning grounding conductor size, for a panel board breaker size of 150 amps, the required grounding conductor size is number 6 equipment grounding conductor. Based on these calculations, the following conductor configuration would meet the requirements. For the run from the panel board to the starter, use number 3 THHN/THWN-2 conductors as ungrounded conductors and number 6 THHN/THWN-2 conductor as a grounded conductor. From the starter to the motor, also use number 3 THHN/THWN-2 conductors as ungrounded conductors and number 6 THHN/THWN-2 conductor as a grounded conductor. To elaborate further on motor circuit conductor sizing, Article 430 of the National Electrical Code, or NEC, provides detailed requirements for motor circuits. Section 430.22 specifically addresses the sizing of conductors supplying a single motor. This section mandates that the conductors have an opacity of not less than 125% of the motor's full load current or flow rating. The full load current for a 50 horsepower motor operating at 480 volts, 3-phase, can be found in NEC table 430.250. According to this table, the FLA is 65 amps. Multiplying 65 amps by 1.25 gives us 81.25 amps. This means the conductors must be sized to handle at least 81.25 amps. Standard conductor ampacity tables, such as NEC table 310.16, provide the allowable ampacities of various conductor sizes based on insulation type and temperature rating. For example, a number 3 copper conductor with THHN insulation, rated for 75 degrees Celsius, typically has an ampacity of 100 amps. Since 100 amps exceeds the required 81.25 amps, a number 3 conductor would be suitable for this application. It is crucial to select conductors with the appropriate insulation type and temperature rating for the specific installation environment. Factors such as ambient temperature, conduit fill, and grouping of conductors can affect the allowable ampacity. Correction factors and adjustment factors, as outlined in NEC table 310.15, must be applied when these conditions exist to ensure the conductors are not overloaded. Next is overcurrent protection. NEC section 430.52 governs the overcurrent protection requirements for motor circuits. This section specifies the maximum size of the overcurrent protective device, such as a circuit breaker or fuses, based on the motor's FLA and the type of motor. For a standard motor, the overcurrent protection device must not exceed 250% of the motor's FLA. In this case, 250% of 65 amps is 162.5 amps. Therefore, a 150 amp breaker is acceptable since it is less than 162.5 amps. The overcurrent protective device is intended to protect the motor and the conductors from overloads and short circuits. It is essential to select a device with an appropriate interrupting rating to safely clear any fault currents. The interrupting rating of the breaker must be sufficient for the available fault current at the panel board. Now let's look at grounding. NEC section 250.122 specifies the size of the equipment grounding conductor, or EG, for motor circuits. The size of the EGC is based on the rating of the overcurrent protective device in the circuit. For a 150 amp breaker, NEC table 250.122 requires a number 6 copper conductor to be used as the EGC. The EGC provides a low impedance path for fault current to return to the source, facilitating the operation of the overcurrent protective device. It is crucial to properly bond the motor frame and any metallic enclosures to the EGC to ensure personnel safety. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the grounding path is minimized, which is important for effective fault clearing. Furthermore, it is important to consider voltage drop in motor circuits, especially for longer runs. Excessive voltage drop can cause the motor to operate inefficiently, overheat, and potentially fail. NEC Section 215.2 provides recommendations for voltage drop in feeder circuits. While not strictly mandatory, it is generally recommended to limit voltage drop to no more than 3% for power circuits and 5% for lighting circuits. To calculate voltage drop, the following formula can be used. Voltage drop equals 2 times K times I times D divided by Cm, where K is the constant representing the direct current resistance for the conductor material, typically 12.9 ohms per circular mil-foot for copper. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mil area of the conductor. For number 3 copper conductor, the circular mil area is approximately 52,620 circular mils. By calculating the voltage drop, you can determine if the selected conductor size is adequate for the length of the run. If the voltage drop exceeds the recommended limits, you may need to increase the conductor size to reduce the resistance. In addition to the NEC requirements, local codes and regulations may also apply to motor circuit installations. It is essential to consult with the local electrical inspector to ensure compliance with all applicable codes. Proper labeling and documentation are also crucial for motor circuits. The panel board and motor starter should be clearly labeled to indicate the circuit number, motor horsepower, and other relevant information. A wiring diagram should be provided to show the connections between the panel board, starter, and motor. Finally, it is important to emphasize that working with electrical systems can be dangerous. Only qualified and licensed electricians should perform motor circuit installations and repairs. Always de-energize the circuit before working on any electrical components and follow all safety precautions. To recap, for a 50 horsepower, 480 volt, 3-phase motor circuit, the minimum conductor size should be number 3 copper with THHN insulation, based on 125% of the motor's full load current. The overcurrent protection device should not exceed 162.5 amps, making a 150 amp breaker suitable. A number 6 copper conductor should be used as the equipment grounding conductor. Always verify these calculations and conductor selections with a qualified electrician and consult the latest edition of the NEC for the most up-to-date requirements. Remember to consider factors such as ambient temperature, conduit fill, voltage drop, and local codes when designing and installing motor circuits. Safety should always be the top priority when working with electricity. It's important to note that the specific requirements for motor circuit installations can vary depending on the application and local codes. It is always best to consult with a qualified electrician to ensure compliance with all applicable regulations and to ensure the safety and reliability of the electrical system. Other considerations can come up too, such as harmonic distortion. Harmonic distortion can be a concern in motor circuits, especially with variable frequency drives, or VFDs. Harmonics are currents and voltages with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz. These harmonics can cause overheating of conductors and equipment, as well as interference with other electrical systems. To mitigate harmonic distortion, you may need to use harmonic filters or reactors. These devices are designed to reduce the amplitude of harmonic currents and voltages, improving the power quality of the system. Another consideration is surge protection. Surge protection devices, or SPDs, can protect motor circuits from voltage surges caused by lightning strikes or switching transients. These surges can damage the motor and other electrical components. SPD should be installed at the panel board and at the motor starter to provide comprehensive protection. Also, power quality monitoring is another consideration. Power quality monitoring can help to identify and diagnose power quality problems in motor circuits. Power quality monitors can measure voltage, current, harmonics, and other parameters, providing valuable data for troubleshooting and maintenance. Additionally, preventative maintenance is key. Regular preventative maintenance can help to ensure the reliable operation of motor circuits. This includes inspecting conductors, connections, and overcurrent protective devices. It also includes testing the motor insulation resistance and performing other diagnostic tests. Finally, energy efficiency is also important. Energy-efficient motors and VFD can help to reduce energy consumption and operating costs. These devices can also improve the power factor of the system, reducing losses and improving overall efficiency. Therefore, in summary, designing and installing motor circuits requires careful consideration of various factors, including conductor sizing, overcurrent protection, grounding, voltage drop, harmonic distortion, surge protection, power quality, preventative maintenance, and energy efficiency. It is always best to consult with a qualified electrician to ensure compliance with all applicable codes and to ensure the safety and reliability of the electrical system.